Well, here we are with Lesson B, Kinetic Theory of Matter. This is our first video for this lesson. It's called the Ideal Gas Model, and so we're going to explore the ideal gas model. Here we go. So all this time we've been talking about thermodynamics. We've been using the kinetic theory of matter to explain thermal energy and the transfer of heat from one system to another. So kinetic theory is the explanation of properties of a gas in terms of randomly moving particles. The kinetic theory can be used for all states of matter, solids, liquids, or gases, but we're going to concentrate here on gases. This leads to the theory often being called the ideal gas model. And these are the assumptions for that theory. You need to be familiar with what these assumptions are. First, we need to assume that the number of particles in a system is huge, and the separation between those particles is huge in relative to the size of those particles. All of those particles move around randomly, and they have perfectly elastic collisions with each other and other atoms. There are no forces of attraction between the particles of a gas, okay? And all the particles are identical. Now, if you've taken chemistry, one of the things that you will have covered in that class is the concept of the mole. A mole is simply Avogadro's number of a thing. It's like a dozen. The word dozen is just a word that signifies 12 of something. A mole is just a word that signifies Avogadro's number of a thing. Avogadro's number is 6.022 times 10 to the 23. So it's just a huge number of things. Now, the number of moles present in a sample of something is really pretty easy to calculate. You just take the number of particles of that thing, divide by Avogadro's number, and you've got the number of moles. Just like you can take, 54 eggs, divide by 12, you have how many dozen eggs you've got. Now, in chemistry, you probably also learned about molar mass. Molar mass of a substance, which is this m mole there, is the mass in grams of 1 mole of a substance. So, to a good approximation, the numerical value of the molar mass equals the numerical value of the atomic or molecular mass. So, for example, the molar mass of helium with a mass of 4 AMU, or atomic mass units, is 4 grams per mole. And the molar mass of a diatomic oxygen, right? A diatomic molecule is a molecule that has 2 of the same molecule bonded together, right? So a molar mass of O2 would be 32 grams per mole. So you can use the molar mass to determine the number of moles. In one of the few instances where the proper units are grams rather than kilograms, the number of moles contained in a system of mass consisting of atoms or molecules with some molar mass then is this right here. This will give us the moles of a substance in terms of its mass, where you take the mass in grams of that substance, divide by its molar mass, and you get the number of moles. Okay, and as another example here, we've got 1 mole of helium, sulfur, copper, and mercury pictured here. There's the helium, there's sulfur, there's copper, there's mercury. You can see that 1 mole of each of those things, their volume is different. Now, speaking of volume, let's take a look at volume for just a second here. Volume is an important property that characterizes a macroscopic system. Okay, it's the amount of space that system occupies. So the SI unit of volume is cubic meters. Even so, both cubic centimeters and to some extent liters are widely used metric units of volume. In problem solving, in most cases, you must convert those to cubic meters before doing any calculations. So now, while it's true that 1 meter equals 100 centimeters, it's not true that 1 cubic meter equals 100 cubic centimeters. The picture here shows that the volume conversion factor is 1 cubic meter equals 10 to the 6 cubic centimeters. So a liter is 1,000 cubic centimeters. So 1 cubic meter equals 10 to the 3rd liters. A milliliter is the same as 1 cubic centimeter. So the atomic model of an ideal gas is based on random motion. So it's no surprise to us that individual atoms in a gas are moving at different speeds. This picture here shows data from an experiment to measure the molecular speeds in oxygen gas at 27 degrees Celsius, which is 300 Kelvin. The results are presented as a graph in which the height indicates the probability of molecules having a speed in the range of speeds shown on the x-axis. For example, the most probable speed here shown here is about 400 meters per second, which is really fast. That's 1,100 miles per hour. Now, because temperature is related to the average kinetic energy of the atoms, it's going to be useful to calculate the average kinetic energy for this distribution. An individual atom of some mass and some velocity has kinetic energy 1/2 mv squared. So an individual atom is going to have the kinetic energy 1/2 mv squared. Now remember that the average of a series of measurements is found by adding all the values and then dividing by the number of data points. In the same way, we can find the average kinetic energy by adding up all the kinetic energies of all the atoms and then dividing by the number of atoms. Now this quantity here, the sum of v squared over n, is the sum of the values of v squared for all the atoms divided by the number of atoms. By definition then, this is the average of the squares of all the individual speeds, which we've written as v squared average. The square root of this average is about how fast a typical atom in the gas is moving. Because we'll be taking the square root of the average, or the mean of the square root of the speeds, we define the root mean square speed as square root of v squared average. This is the speed then of a typical atom. Now, the root mean square speed, or the RMS speed, is not the average speed of atoms in the gas. It's the speed of an atom with the average kinetic energy. But the average speed and the RMS speed are very nearly equal, so we can interpret an RMS speed as telling us the speed of a typical atom in the gas. So by rewriting this equation in terms of the RMS speed, it gives us the average kinetic energy per atom. Now remember how we've talked about temperature being related to the average kinetic energy of the atoms in the gas. That temperature is related to the average kinetic energy of the atoms in the gas by this equation here, where this is the average kinetic energy, the T is the temperature. This K sub B is known as Boltzmann's constant. Okay, the Boltzmann's constant has a value of 1.38 times 10 to the negative 23 joules per Kelvin. And this equation tells us how temperature measures the average kinetic energy of the particles in a system. Now, since we have two equations then for average kinetic energy, we can equate them and solve for temperature, and we get this here. Now, when we solve this for the RMS speed, we get this equation here. Two really important things to remember when using this equation is we've got the T here is the temperature in kelvins, and the M down here is the mass of a single particle of that gas. We have to use the absolute temperature in kelvins to compute RMS speeds. Now, we've been considering ideal gases made from atoms, but these results are equally valid for real gases made of either atoms or molecules. At any given temperature, this equation is going to show the speed of atoms or molecules in a gas varies with atomic or molecular mass. A gas with lighter atoms will have faster atoms, on average, than a gas with heavier atoms. This equation also shows that higher temperatures correspond to faster atomic or molecular speeds. The RMS speed is proportional to the square root of the temperature. We're going to go from here then, we're going to talk a little bit more about pressure and go into what's called the ideal gas law, and we'll do that in the next video. See you then.